Okay, so I guess perhaps some of you have thought about this during the break. So my question here pertains to what would you respond to someone coming up to you and saying, okay, look at this, I found a flaw in the theory of relativity, because this, according to this time dilation phenomena, we should encounter or be faced with a paradox for the aging of these twins, because time should be measured differently as seen from the different twins when they return. So someone comes up to you and says, okay, I have found a major flaw in the theory of relativity. So what would you respond?
Twin B has to be subjected to an acceleration during his trip, so he leaves his inertial reference frame.
Okay.
So his time can't be regarded as an eigentime.
Very good. That is exactly the sort of condition that breaks the postulate of this special theory of relativity, namely that we're operating now with different, he's changing inertial system. First of all, he has to accelerate to a velocity v, and then he has to change direction, which for sure involves an acceleration of some sort, even if the velocity is constant. So the point here is that you can't use these transformations naively, as we've done here, because we're dealing with a change of inertial systems. We're dealing with accelerated systems, in which case we know that we should turn to the general theory of relativity, not the special one. So I just wanted to illustrate the fact that this isn't a proof for that the special theory of relativity is inaccurate or wrong. We just have to recognize the fact that we're dealing with a situation that breaks this condition of having reference systems that move with a relative constant velocity. We'll have a look at one more example. Just to give you an idea of the numbers involved in experiments where you typically would like to measure this time dilation effect. In principle, time dilation should be present for any moving object. So moving clocks run slower, right? So as I move, as I walk here, I'm subject to a time dilation effect. It's a very tiny effect because my speed isn't comparable to the speed of light at all, but there is an effect nonetheless. So if we want to measure this effect, we would like to have an object moving at as large velocity as possible compared to the speed of light. And airplanes move reasonably fast, so it's possible that we might be able to measure actually the time dilation effect in airplanes by using extremely accurate watches, such as these cesium atomic watches. So if you place one of these watches in an airplane and then measure the time dilation effect, typical numbers would look something like this. The velocity of the airplane, let's say 500 kilometers per hour, as a ballpark estimate. Well, that's 140 meters per second, and if you plug that into the formula for gamma, where you have the ratio between the velocity and the speed of light, you get a gamma factor which is 1 plus 10 to the power of minus 13. So there's a very small effect, but it might be measurable. Assume that this airplane is in motion for 11 hours. If it's traveling for 11 hours, we know that the eigentime here is related to the time t in the following way by this gamma factor. And if we divide on a very small number, then we can use the following expansion. So basically the correction to, or the difference between a clock in the plane and a clock on Earth, measuring how long the airplane has been absent or traveling, is 4 nanoseconds. Okay. So in other words, the clock in the airplane has slowed down about 4 nanoseconds compared to a clock on Earth. And 4 nanoseconds, small as it might seem, is actually measurable. So you can actually measure this time dilation effect by using an airplane. Now, I started by discussing a bit this Lorentz invariance of the laws of physics. And then we moved on to introducing these phenomena of time dilation and length contraction. Now, before returning to this discussion of how physical theories have to be Lorentz invariant, I would like to introduce one more concept, namely how we can classify different position 4 vectors, because we'll use that, and also these concepts of eigentime and the concept of eigentime when discussing the Lorentz invariance of physics. So there are different ways that we can classify 4 vectors x mu. Namely, we can classify the position 4 vectors as space-like if their square or their scalar product is positive, time-like if it's negative, whereas it's null, or light-like if it's exactly equal to 0. And in order to understand why we use this terminology to classify these 3 scenarios, consider the following. Consider the following scenario. We have 2 events, and an event in general we can think of as a coordinate in Minkowski space. An event, for instance me walking along this blackboard, is characterized instantaneously by a position vector and a time coordinate. Right? My position vector relative to this room, for instance, and the time at which I'm walking. So that's one event. And we have 2 of these events. Consider now the difference between these 2 events. So we construct a vector large x mu, which is equal to the difference between the position 4 vectors of these 2 events. In other words, the norm of this vector will be the following. Again, without any real loss of generality, we choose our coordinate system so that the difference between the position vectors of the 2 events, 1 and 2, is directed or parallel with the z-axis. So we have 2 events. Their spatial coordinate, the difference between their 2 spatial coordinates, is directed along some z-axis. Now imagine that we have some reference system S prime, which is moving with the velocity v relative to this z-axis. In this case, we know that the transformation from the stationary system to the moving system is given like this. So the difference in time at which these two events occur, as seen from a moving observer, is provided by this expression. It depends on the difference in time at which the events occur as seen from a stationary observer, but also this second term depending on the position at which it occurs due to the relativistic consideration. I can rewrite this term slightly. Like this. Now, to see where this terminology space-like, time-like, and null, or like-like, stems from, consider first the case where this difference vector, large x mu, is space-like. In that case, we know that the norm is positive. In other words, we have the following, based on this expression here. So if it's larger than 0, I'm just moving this term over and taking the square root. So I get this. Now, let's make this even more concrete. Let's say I'm a baseball player. I'm standing on the field. The first event is that I hit the ball with a bat. That's event x1, characterized by this spatial coordinate and this time coordinate. The second event is that the ball hits the grass on the field. So we're considering these two events. They have different position vectors and different time coordinates. Now, obviously, as seen from my system, T1 is smaller than T2. I hit the bat, the ball lands. So now my question to you is the following. Will this be the case in all coordinate systems? In other words, regardless of which inertial system I'm in other words, regardless of which S prime I'm in, even if I'm moving with velocity v, will I always see this cause effect that I hit the ball with the bat and the ball lands? So if T1 is smaller than T2, does this mean that T1 prime is smaller than T2 prime in any inertial system? So take a minute to think about that. Any ideas, comments? So we're basically discussing a pretty deep philosophical question here, namely the principle of causality, cause and effect. So in other words, I hit the ball at T1, the ball lands at T2. But is this what is seen by all observers? Do they always see that hitting the ball occurs before the ball lands? So let me give you a hint. We have this relation for a space-like vector. And we have the following transformation between the time observed in a moving inertial system and the coordinates in our stationary system. So this is general. This is for the particular case of a space-like difference vector. So based on these two equations, can you infer if this statement is correct?
As long as Z2 is greater than Z1, it will be true.
Okay. So you mean that, sorry? So if Z2 here is greater than Z1, it should be true. Yeah. Okay, let's check. So we have that the absolute value here, we can rewrite this equation as, well, let's rewrite this rather. Okay, so we have the following. Now this beta parameter varies between 0 and 1. Do you agree? It's the velocity divided on c. So it's either 0 or it's maximum 1, or it can go towards 1. Now we have that this should be true, according to a space-like vector. So this term is always smaller than this parenthesis here. But we have an additional modifying factor beta here, right? Which is adjustable because we can choose the velocity of this thought inertial system. So if this is the case, well, we should be able to tune this parameter beta in order to adjust the relative size of this contribution and this contribution. In fact, if I make beta sufficiently small, by choosing this sufficiently close to 0, this term should be greater than this term. Do you agree? So in fact, we can, based on this observation, we can always choose a velocity beta here such that these two terms are equal to each other. This term is always smaller than this term, but with the additional modifying beta factor here, I can choose v and hence choose beta in order to adjust this contribution so that it becomes equal in magnitude to this contribution. Do you follow? So in other words, if I then can do this, well, and this has the rather unsettling consequence that the difference between the time coordinate of these two events should be 0. In other words, the events should be simultaneous. They should occur at the same time. So let me try to illustrate this more clearly. Let's say this value here is 0.5 in some unit. Let's say this value here is 0.9 in some unit. Well then, if I choose beta as 1/2, so I choose an inertial system with a velocity so that beta becomes 1/2, well, this becomes larger even than this one. So we can actually tune with beta which event occurs first. In other words, causality is completely lost. Even though I hit the ball with bat before it lands in our coordinate system, I can find a different coordinate system moving relative to us where the ball lands before I hit it with the bat, or that they occur simultaneously. So space-like separation of two events seems a bit scary, because it means that we can't actually say with 100% certainty which event that occurs before the other. We can't say anything about cause and effect, because what looks like it happens before the other event in one system could be reversed in another system. So let's consider the second case now, where x mu is a time-like vector, meaning that its norm is negative. Or, put differently, we have the following relation, which follows from the definition of x mu over there. So using the same type of argument that we did for the space-like vector, what can we say about this causality effect for time-like separation? Any ideas? So again, consider the expression for the time difference between events in a moving coordinate system, or a different inertial system. We now have that this term is always greater than this parenthesis. Now, this modifying factor takes a value from 0 to 1. So it means that the maximum value of beta multiplied with z1 minus z2 is z1 minus z2. But this term is always greater than z1 minus z2 according to that. So in other words, we cannot find an inertial system if the separation is time-like where the two events can be perceived simultaneously. So events with space-like separation can be made simultaneous in some inertial system. In other words, the classification before and after has no meaning. But for events with a time-like separation, these may not be perceived as simultaneous in any inertial systems. In other words, if T1 is greater than T2 in some system, then T1 must be greater than T2 in all systems. So before and after are now uniquely defined again. And we have restored causality, you may say. All right, so armed with these concepts now, time dilation, length contraction, and this classification of the four vectors, in particular distinguishing events with a space-like and time-like separation, we'll now start on the Lorentz invariance of important laws in physics, or theories of physics. So a couple of tools that we will use when analyzing these theories is, for instance, the four velocity. And it's defined as the derivative of the four position vector with respect to the eigentime tau, which is a Lorentz invariant quantity. So to evaluate what this four velocity is, consider the differential of the four position vector x mu. It's dxi ic dt. So I'm using here Roman indices on the dx to indicate that this is only for the spatial dimensions. So for the first three components of the four velocity vector, we have the following relation, where I have now used how the eigentime is related to the time measured by a moving observer, and they're proportional by this gamma factor. So that leaves us with the fourth component, namely this. So this is the four velocity vector. So you see we have an extra gamma here compared to the non-relativistic velocity, and you have IC as the fourth component. Okay, so this four velocity vector. Now, our discussion just a couple of minutes ago about this time-like and space-like classification of the vectors showed us that time-like vectors made more sense in terms of having this causality intact that you could uniquely define before and after. So check if this four velocity vector is space-like or time-like. You can do that in half a minute. So what did you find? Is it space-like or time-like? What's the conditions? If it's space-like, all right. And opposites for the time-like case. So then the question is simply, what happens for this four vector?
I think it's space-like.
Space-like, okay. Let's try to multiply. So we have u mu, it's gamma v squared plus gamma IC squared. Do you agree? Mm-hmm. So we should have this. So do you still think it's space-like? No. It's actually time-like. Because it's negative. Well, we can see it immediately here actually. This is a positive quantity and V has to be smaller than C. So basically, this is a time-like vector and it should behave reasonable. Okay, so that was the for velocity. Now there's an important sort of continuity equation in physics, which you might have seen before. Namely, it's a continuity equation for charge, and it has a very general form, which you can actually transfer to other types of quantities. J here is the current density vector and rho is the charge density, so it's a scalar. It's the amount of charge you have per unit volume. What this equation states is that the time derivative, that if there's a change in the charge density with time, then there has to be a belonging either inflow or outflow of charge. If there's no change in the charge with respect to time, then this is zero. So there's either no charge streaming in and out of the system, or there's equally much going in as out. So this continuity equation for charge basically gives us a relation between the time variation of charge and sort of the flux of charge. And this is a quite general form. You will see this form for many other types of quantities. And so this is an example of one of those laws of physics that should be Lorentz invariant. It should look the same in any inertial system. Now we can write this continuity equation even more compactly by introducing this 4-vector J mu, which has its first 3 components, simply the current density, and its 4th component, IC rho. By using this definition and also the definition of the 4-position vector, you can show that the derivative of this with respect to x mu gives you precisely this equation here. And just notation-wise, we often write the partial derivative of J mu as simply del mu. So del mu, j mu should be equal to 0. So we'll continue with this tomorrow.